What if the universe is teeming with life, yet we are simply not looking in the right places? What if, among the countless stars above, there exists a planet so similar to Earth that it could be our mirror image across the cosmos? And what if we are on the verge of uncovering secrets that will forever redefine our place in the universe? For centuries, humanity has gazed at the night sky, seeking answers to the fundamental questions of existence. Where did we come from? Are we alone? And how vast, truly, is the cosmos? Science has propelled us from mere observers to explorers, giving us tools to peer into the very fabric of reality. And in just the past few decades, we have made discoveries that were once confined to the realm of science fiction. Take, for example, the groundbreaking revelation of 2017, 7 Earth-like planets orbiting a single star just 39 light-years away. 7. A number that was once the stuff of imagination, now a confirmed reality. These rocky worlds, circling the ultra-cool dwarf star TRAPPIST-1, could hold atmospheres, liquid water, and perhaps, just perhaps, the conditions necessary for life. And if that weren't enough, in the very same period, astronomers found Proxima Centauri b, an Earth-sized exoplanet orbiting the closest star to our own, a mere 4 light-years away, a cosmic neighbor in every sense. Each of these discoveries is another entry in the ever-growing catalog of over 5,000 exoplanets, worlds beyond our solar system, each unique, each carrying the possibility of the unknown. But exoplanets are just the beginning. In 2019, for the first time in human history, we saw the unseeable, a black hole, photographed in stunning clarity, proving Einstein's century-old predictions right. A monstrous abyss, 6 billion times the mass of the Sun, bending space and time itself, captured by an array of telescopes working together as one. Yet, even that pales in comparison to what came next. The launch of the James Webb Space Telescope in late 2021. With its unmatched precision, it has delivered images that have left even the most seasoned astronomers in awe. Galaxies from the dawn of time, the chaotic beauty of nebulae, the whisper of light that has traveled for over 13 billion years to reach us. And this is only the beginning. The universe is revealing itself to us, piece by piece, and with each new discovery, we come closer to answering the age-old question: are we alone, or is life an inevitable consequence of the cosmos? A glimpse from the ancient world, the birth of cosmic thought. Let us embark on a journey through time, an intellectual voyage to the origins of humanity's understanding of the cosmos. Imagine yourself in ancient Greece, a world devoid of telescopes, satellites, or scientific journals. If you had no prior knowledge of the universe, how would you perceive it? You stand on firm ground, which appears unmistakably flat, save for the mountains and valleys. Above you stretches a vast unbroken dome of blue, adorned with the sun, the moon, and an intricate pattern of stars. The world around you is wild, governed by nature's cycles. Each morning, from the eastern edge of the sky, a blazing orb emerges, the sun. Its warmth dictates the rhythm of life, rising to its zenith before gradually descending beyond the western horizon. With its departure, the world plunges into darkness, revealing a celestial tapestry of stars, whose configurations remain unchanged night after night. Yet, amidst this apparent constancy, there are exceptions. 5 bright celestial bodies move against the starry background, tracing curious loops across the sky. The Greeks named them planetae, wanderers, honoring them with the names of their most revered deities: Mercury, Venus, Mars, Jupiter, and Saturn. These luminous enigmas, along with the rhythms of the seasons, eclipses, and tides, were not merely celestial phenomena. They dictated agriculture, navigation, and survival itself. The first step toward understanding the universe was recognizing its predictability. Ancient observers noted that the seasons followed a strict order. Spring never gave way to winter. Summer always preceded autumn. Over time, they realized that these cycles were not arbitrary, but governed by fundamental rules. The ability to anticipate celestial events marked a profound intellectual leap, from passive observation to structured reasoning. Ancient civilizations sought explanations for these cosmic patterns through the framework of the 4 classical elements: earth, water, air, and fire. The Chinese tradition added wood and metal to this system, The world, they believed, was composed of varying mixtures of these elements, with divine forces overseeing their harmony. Given the limited observational tools of the time, it was only logical to assume that the Earth was a flat disk, covered by a solid dome of the heavens. The rain came from water reservoirs in the sky. The sun and moon traveled across the firmament, and the stars were perceived as pierced holes in the celestial shell through which the light of the heavens shone. Similar notions appeared across cultures. The Old Testament described a firmament separating the earthly waters from the heavenly ones, with celestial bodies embedded within it. The idea of a foundation supporting the earth was widespread. Some envisioned massive creatures such as elephants, turtles, or bulls holding it aloft. Others imagined the world floating on an endless ocean, tethered to the heavens by divine chains. In Islamic tradition, the earth rested upon a layered structure of an angel, a bull, a ship, and a great fish, while Slavic myths spoke of an oak tree and sea-dwelling whales as cosmic supports. However, such models faced a fundamental logical flaw. They required an infinite regress of supports. If the earth rested on something, what held that support? And what held that? At some point, the chain had to stop. Eventually, thinkers began to realize that invoking divine intervention at every step was an unnecessary complication. Would it not be simpler to assume that the Earth simply floated freely in space? This groundbreaking idea first emerged in the 6th century BCE, proposed by the Greek philosopher Anaximander. In his view, the Earth was not held up by anything. It remained motionless in space, perfectly balanced in the center of the universe. His reasoning was striking in its elegance. If the Earth were truly at the cosmic center, there would be no reason for it to move in any direction. This was a monumental intellectual breakthrough, to imagine that the vast landmass beneath our feet, with its mountains and oceans, could exist unsupported in the void. It may have seemed counterintuitive, but it was still a far more rational model than an infinite stack of elephants and turtles. Anaximander also made an early attempt to explain the structure of the cosmos. He envisioned the universe as being composed of concentric rings of fire, each encircling the Earth. These rings, partially obscured, had openings, small gaps through which the cosmic flames shone. The smallest opening was the stars, the next was the moon, and the largest, the sun, appearing as a massive fiery portal. His ideas were speculative, yet they contained the seeds of a revolutionary thought. Celestial bodies exist at varying distances from Earth. Even more remarkably, Anaximander suggested that life originated from water. He believed that in the primordial world, the Earth was covered in a moist, fertile mud from which early creatures emerged. These beings, resembling fish, eventually adapted to land, giving rise to the first humans. While purely hypothetical, this concept eerily foreshadowed the principles of evolution, an astonishing achievement for an age ruled by myth and superstition. While Anaximander's ideas were bold, it was Pythagoras who brought mathematical precision to cosmology. In the 6th century BCE, Pythagoreans believed that the fundamental nature of reality was mathematical harmony. Pythagoras discovered that musical notes could be derived from simple ratios of string lengths, leading to the radical idea that the entire cosmos must be governed by numerical laws. This belief shaped their vision of the universe. At the center of everything, they imagined a mystical, central fire around which all celestial bodies revolved, including the Earth. Between the Earth and this central fire, they postulated the existence of an invisible counter-Earth, forever hidden from view. Surrounding this system were 10 celestial spheres, each carrying a planet or star. These spheres rotated at different speeds, generating what the Pythagoreans called the music of the spheres, a cosmic symphony imperceptible to the human ear. Their system was deeply flawed. It relied on invisible forces in crystal spheres to hold celestial bodies in place. Yet, it was the first to suggest that Earth was not the center of the universe, but merely one of many celestial objects in motion. The idea that the Earth could rotate, explaining the cycle of night and day, was a remarkable insight, one that would not be fully accepted until Copernicus, over 2 millennia later. As we trace these ancient theories, we see the gradual emergence of scientific thought. While early models were often based on speculation, they represented a crucial shift, an attempt to explain the universe without relying solely on mythology. Though primitive, these ideas laid the groundwork for the rational investigation of the cosmos. The dawn of science, the first steps. What unites all these ancient theories, from biblical cosmology to Pythagorean speculation? You may have already guessed. Indeed, they were largely products of human imagination. While they often stemmed from careful observations, much of their content was based on conjecture rather than rigorous reasoning. As a result, many of these early ideas turned out to be incorrect. There is no flat Earth, no celestial firmament, and no crystalline spheres emitting the music of the cosmos. Yet, what allowed humanity to distinguish truth from fiction? The answer appears to lie in the emergence of critical thinking, the foundation upon which the scientific method was built. Humans began scrutinizing their own ideas, asking themselves, why do I believe this? Could it be otherwise? What if lightning is not the wrath of Zeus, but something else entirely? Critical thinking became the engine of civilization's progress. Take, for instance, the texts of ancient Egypt and Babylon. While these civilizations achieved remarkable advancements in mathematics, they lacked the very concept of proof. Their calculations were practical rather than theoretical, primarily designed for accounting, engineering, and astronomy. Proofs, as a formalized system of logical demonstration, emerged in ancient Greece over 2,500 years ago, likely influenced by the rise of democratic debate. In the assemblies of aristocratic equals, persuasive reasoning, logic, and competing viewpoints were essential. Victory in argument belonged not to the one adorned with the most laurels, but to the one who presented the most compelling evidence. It was this emphasis on reasoned argument that led to the birth of mathematical theorems. Thales, one of the earliest Greek mathematicians, was already proving geometric principles, such as the equality of base angles in an isosceles triangle. Mathematics became an esteemed intellectual pursuit, an elite domain of rigorous thought. It is no wonder, then, that the Greeks soon developed an entire system of geometry, a structured approach that would influence human understanding for millennia. In the 4th century BCE, Aristotle was among the first to apply a systematic scientific approach to understanding the cosmos. Observing the moon, he deduced the nature of its phases. The moon was a sphere illuminated by sunlight. Studying lunar occultations of Mars, he correctly inferred that planets must be farther than the moon, while stars lay even farther beyond. But perhaps his most remarkable contribution was his 3 arguments for the Earth's sphericity. First, he noted that as a ship sailed away from shore, the hull disappeared from view before the mast, a phenomenon only possible on a curved surface. Second, during lunar eclipses, the Earth's shadow cast upon the moon was always circular, regardless of the observer's location. Only a spherical Earth could produce such a consistent shadow. Third, the elevation of the North Star changed with latitude. As one moved northward, the star rose higher in the sky. This observation could only be explained if the Earth's surface was curved. Through these logical deductions, Aristotle provided an argument for Earth's roundness that remained unchallenged for centuries. Yet even Aristotle, for all his intellectual brilliance, erred in believing the Earth to be the center of the universe. His reasoning was grounded in careful observation. If the Earth moved around the Sun, he argued, then the stars should exhibit a shift in position, what we now call stellar parallax. However, because stars are so unfathomably distant, this parallax was imperceptible to ancient instruments and was only measured in the 19th century. Given the observational limitations of his time, Aristotle's conclusion that the Earth was stationary seemed entirely reasonable. 4 centuries later, Aristotle's cosmological ideas found their full expression in the Ptolemaic system. Claudius Ptolemy sought to reconcile theoretical models with empirical observations. To explain planetary motion, he devised an elaborate system of epicycles, circles upon circles, along with deferents, which were larger circles governing the motion of these epicycles. The complexity of this model was staggering. Epicycles nested within deferents, deferents within other epicycles, creating a dizzying, almost fractal-like arrangement. In a way, Ptolemy did not just create the geocentric model, he might have inadvertently invented the world's first conceptual matryoshka doll. Yet, despite its convoluted structure, the Ptolemaic system worked. It predicted planetary positions with remarkable accuracy, allowing astronomers to forecast celestial events years in advance. And Ptolemy was no mere theorist. He understood the implications of inertia and centrifugal force, yet lacking precise equations and experimental validation, he reasoned that a rotating Earth would cause objects to be left behind. He believed that if the Earth spun, falling objects would veer off course and clouds would drift uncontrollably. It took 1,700 years before experiments like Benzenberg's proved that the Coriolis effect, though subtle, was indeed real. What made the Ptolemaic system different from previous cosmological models was its foundation in rigorous observation and logical structure. It was not mere speculation, but an attempt to reconcile nature's apparent motion with mathematical precision. However, as science evolved, it ultimately refuted this model. Yet for 1,500 years, the Ptolemaic system remained the dominant worldview in Europe, a testament to both its ingenuity and the inertia of established thought. The sun at the center of the universe. For centuries, Greek observations seemed to confirm that at the heart of the cosmos lay a motionless, spherical Earth. Could no one have dared to challenge this assumption? Some indeed did. Among them was Aristarchus of Samos, who long before Ptolemy devised a method to measure the distances to the sun and the moon. Observing the moon during its first or last quarter, when exactly half of its disk is visible, Aristarchus reasoned that the angle between Earth-Moon and Moon-Sun directions must be a right angle. From this, he deduced that the ratio of the Earth-Moon distance to the Earth-Sun distance equaled the cosine of the measurable angle between the two directions. His calculations estimated that the Sun was 20 times farther than the Moon. Since the apparent sizes of the Sun and Moon are roughly the same, this implied that the Sun must be at least 20 times larger than the Moon. By comparing the relative dimensions of Earth's shadow on the Moon during eclipses, Aristarchus further estimated that the Earth was about 3.5 times larger than the Moon, an approximation close to the true value. From these calculations, one staggering conclusion emerged. The Sun was not only larger than the Moon, but also significantly larger than the Earth, by a factor of at least 6, and hundreds of times more in volume. This realization led Aristarchus to a groundbreaking hypothesis. What if the vast Sun, rather than the smaller Earth, was at the center of the universe? The variation in Mars' brightness, which the geocentric model struggled to explain, further supported this idea. As for the lack of observable stellar shifts due to Earth's motion, Aristarchus postulated that the stars must be incomprehensibly distant, a claim that was entirely correct. Yet, despite its elegance, his heliocentric model could not compete with the mathematically refined Ptolemaic system, which, for all its complexity, aligned more accurately with naked-eye observations. By the late 5th century, with the fall of the ancient world and the onset of the Middle Ages, scientific progress stagnated. Not only did knowledge fail to advance, but much of the intellectual heritage of antiquity was lost. The rise of Christianity brought a new worldview, one in which questioning biblical interpretations of the universe was met with skepticism. The works of classical thinkers were often destroyed. The libraries of Alexandria, once a beacon of human knowledge, were reduced to ashes, along with countless invaluable scrolls and manuscripts. To ask challenging questions in such an era was to risk one's life. By the 6th century, the dominant Christian cosmology was epitomized by Cosmos Indicoplistes' primitive model, a flat, quadrangular Earth enclosed by towering walls and a solid celestial vault. Night, according to this view, occurred when the sun dipped behind a massive northern mountain. Even the idea of a spherical Earth faced ridicule. How, after all, could people on the opposite side walk upside down? Later, Aristotle's teachings were selectively embraced by the Church, particularly his geocentric model, which aligned conveniently with biblical notions of Earth's centrality in creation. It was a perfect fit. Earth, immobile and divine, lay at the heart of the cosmos. Any scientific inquiry beyond Scripture was deemed unnecessary, even dangerous. The call for empirical observation and critical analysis championed by Aristotle faded into obscurity, replaced by rote memorization and dogmatic adherence to tradition. Intellectual independence was neither encouraged nor tolerated, and accusations of heresy loomed over any dissenters. Unsurprisingly, the entire medieval period in Europe yielded virtually no significant astronomical discoveries. It was not until the 16th century that the stagnation ended. And who had the audacity to resurrect the heliocentric hypothesis? A clergyman. Imagine, deep in his monastic study, Nicholas Copernicus pored over ancient texts, and suddenly an idea struck him, an idea so simple, so elegant. What if the sun is at the center and the earth revolves around it? The earth in turn rotates on its own axis. This insight instantly explained the peculiar looping motions of planets, apparent retrograde motion that had long puzzled astronomers. Yet, Copernicus was no reckless revolutionary. He spent 40 painstaking years refining his model, ensuring no loophole could be easily exploited by critics. His system preserved the structure of Ptolemy's, but with far fewer epicycles, replacing them with a simpler framework of deference. Most crucially, he inverted the cosmic hierarchy, placing the sun, not the earth, at the center. In his model, planets moved along transparent celestial spheres, nested within one another, with the stars affixed to the outermost sphere. One might liken it to wallpaper decorating the universe's grand dome. Copernicus' work, however, was no easy read. It was dense, mathematical, and at times less precise in its predictions than Ptolemy's model. Nevertheless, its central ideas spread like wildfire across Europe, marking a true paradigm shift. Tragically, Copernicus did not live to witness the impact of his work. He died before its publication. The man who reignited the flame of scientific inquiry never saw the revolution he had set in motion. Thus, the dawn of heliocentrism was not just a triumph of mathematics or astronomy, it was a triumph of reason over dogma, of bold questioning over blind acceptance. The true center of the universe was not Earth, nor even the sun, but the relentless human spirit, ever seeking, ever questioning, ever striving toward the light of knowledge. Is the universe infinite? The transition to a new worldview, known as the Copernican revolution, was nothing short of revolutionary. Consider the implications. Earth was no longer the cosmic center, but merely one of many planets, relegated to the periphery of existence. Humanity, once envisioned as the privileged focal point of creation, had to confront a humbling reality. This shift in perception took centuries to unfold and was met with fierce resistance. At first glance, no new evidence had emerged in favor of heliocentrism. Many of the arguments proposed by Copernicus had already been voiced by Aristarchus of Samos centuries earlier. Initially, the Catholic Church remained indifferent to Copernican theory, viewing it as a convenient computational tool rather than a literal depiction of reality. But soon, the suggestion that Earth was not at the center of the universe took on a dangerous heretical tone. The controversy was further inflamed by the passionate advocate of Copernicanism, Giordano Bruno. Bruno went beyond Copernicus, proposing an infinite universe filled with countless worlds akin to our own. In his vision, stars were distant suns, each potentially hosting orbiting planets, some of which might even harbor life. Such radical ideas, challenging the very foundations of religious dogma, were intolerable to the Church. The result was tragic. In 1600, Bruno was burned at the stake. In 1616, Copernicus' De Revolutionibus Orbium Coelestium was placed on the Index of Forbidden Books. It seemed that heliocentrism was doomed, yet progress proved unstoppable. In 1609, Galileo Galilei, inspired by reports of the Dutch telescope, constructed his own and turned it toward the heavens. His discoveries were revolutionary. Venus exhibited phases like the moon, proving it orbited the sun. Jupiter possessed moons that clearly revolved around it, defying the notion that all celestial bodies circled Earth. These observations provided undeniable evidence in favor of heliocentrism. Why, then, did Copernican theory ultimately prevail despite the Church's opposition? It seems that the intellectual climate of the 17th century was ripe for such a transformation. European society was racked by upheavals. Wars, plagues, and economic crises shattered medieval stability. In such a world, it became difficult to view Earth as the perfect centerpiece of creation. Instead, the Sun, eternal and unchanging, seemed far more suited to occupy the central position in the cosmos. Yet one major obstacle remained on the path to a coherent cosmological model: the assumption that planetary motion must adhere to perfect circles. For centuries, astronomers had resorted to increasingly elaborate systems of epicycles and deference to explain planetary irregularities. Even Copernicus, despite relocating the Sun to the center, had not completely abandoned these constructs. Only in the early 17th century did Johannes Kepler, analyzing Tycho Brahe's precise observations of Mars, uncover the true nature of planetary motion. He formulated his now famous laws, revealing that planets move in ellipses rather than circles, and that their speeds vary, accelerating when closer to the Sun. Kepler's laws provided an astonishingly precise description of celestial motion, eliminating the need for cumbersome epicycles and further solidifying the Copernican model. These laws are often considered the final chord of the Copernican revolution. Yet the true culmination of this revolution was the concept of an infinite universe. As early as the 15th century, Nicholas of Cusa argued that in an unbounded cosmos, no single absolute center could exist, not Earth nor even the Sun. He speculated about an infinite array of worlds. Giordano Bruno expanded on these ideas, asserting that an infinite creator must necessarily have fashioned an infinite cosmos, teeming with stars and planets, some potentially habitable. The notion of infinity, though seemingly abstract, is something we grapple with even in childhood. Consider numbers. There is no largest prime number. One can always add another. Similarly, a spacecraft traveling through space will never encounter a wall inscribed with "End of the Universe." No matter how much time elapses, another moment will always follow. In many ways, imagining a finite universe is more difficult than embracing an infinite one. Newton's theory of gravitation. For centuries, humanity pondered the forces that set celestial bodies in motion. Some believed that the stars and planets moved of their own volition, imbued with a form of life. Others attributed their paths to divine beings, spirits, angels, or gods guiding their motions. But as centuries passed, supernatural explanations lost their persuasive power. A new paradigm emerged: the idea that the universe operates according to impersonal natural laws. Johannes Kepler, who formulated the laws of planetary motion, speculated that planets slowed as they moved away from the Sun because the Sun itself was the source of a mysterious driving force. Around the same time, William Gilbert, a pioneer in the study of magnetism, hypothesized that Earth was a giant magnet, an idea supported by the behavior of compass needles. Some even suggested that Earth's rotation was driven by magnetic forces and that the Moon influenced the tides through magnetism. In 1609, Kepler went even further. What if the Sun itself is a giant magnet? He envisioned solar rotation generating a vortex in the ether, compelling planets to move around the Sun with decreasing speed at greater distances. René Descartes extended this idea into a cosmic model of swirling ether vortices, with stars at their centers. While these theories ultimately proved incorrect, later discoveries confirmed that the Sun does possess a magnetic field that rotates with it. However, planetary motion is not governed by magnetism. The true nature of the forces shaping the cosmos was uncovered by the brilliant Isaac Newton. He realized that the same force that keeps the Moon in orbit is also responsible for pulling an apple toward the ground. If the Moon were to stop moving, it would fall to Earth just as an apple does. But because the Moon possesses immense orbital velocity, it continuously misses Earth, perpetually falling around it instead. Could an apple be transformed into a moon, provided it were given sufficient speed? Newton concluded that it could. If an object were launched with enough velocity, it would enter orbit around Earth, continuously falling but never reaching the ground. To illustrate this, Newton devised his famous thought experiment of a cannon placed atop a mountain where there would be no atmospheric drag. If fired with increasing speeds, the projectile would land progressively farther away. At a certain critical speed, now known as the first cosmic velocity, the cannonball would not fall back at all, but instead orbit Earth in a perfect circle. If fired even faster, it would follow an elongated elliptical path. Once reaching the second cosmic velocity, it would escape Earth's gravitational pull entirely and travel into space. Thus, Newton formulated the universal law of gravitation, a force acting between all masses, diminishing with the square of the distance between them. Though gravitational attraction is most perceptible when at least one mass is immense, like Earth, Newton's law demonstrated that every object in the universe exerts gravitational pull on every other. Through meticulous mathematical analysis of the moon's motion, Newton derived this law, and remarkably, Kepler's 3 laws of planetary motion emerged naturally as consequences of it. His theory operated with extraordinary precision, enabling astronomers to calculate planetary orbits and later even the trajectories of spacecraft with breathtaking accuracy. By the 18th century, enlightened thinkers had embraced this new cosmic vision. The universe was now seen as an infinite expanse populated by countless stars, each potentially hosting planetary systems similar to our own. The force of gravitation governed all celestial bodies, and time flowed uniformly across the cosmos. Yet mysteries remained. Why, for instance, do the planets all revolve around the Sun in the same direction and nearly within the same plane, while comets exhibit chaotic, unpredictable paths? Even Newton found no definitive answer. In the absence of a clear scientific explanation, he resorted to the notion of divine intervention. Perhaps, he speculated, an intentional act of creation had set the planets into their harmonious orbits. What other answer was there at the time? A static cosmos, a universe without change. As telescopes improved, astronomers gathered an ever-growing wealth of data on the distant reaches of the cosmos. What did they find? At first glance, nothing seemed to change on a grand scale. Seasons came and went on Earth, planets and comets traced their orbits around the Sun, and distant stars twinkled in the vastness of space. The universe appeared stationary, what physicists call unchanging in time. While individual stars might extinguish, new ones would ignite in their place, creating an illusion of eternal stability. The cosmos, some believed, was akin to an ocean where waves continuously replaced one another, yet left the surface fundamentally unchanged. Although some medieval thinkers entertained the idea that the universe might evolve, this notion was not widely accepted. Most astronomers of the past sought to understand celestial bodies under the assumption of a static cosmos. A crucial step toward unraveling the structure of the universe involved measuring the distances to stars. The method for this had been theoretically understood since antiquity. By tracking the position of a star multiple times throughout the year, one could detect a small apparent shift, its annual parallax, caused by Earth's motion around the Sun. The smaller the parallax, the farther away the star. For centuries, even the greatest astronomers, including Kepler and Herschel, failed to detect stellar parallax. This emboldened supporters of geocentrism, but Copernicus and his followers remained undeterred, arguing, "No, the stars are simply unimaginably far away." It was not until 1838 that Friedrich Bessel, using the precision optics of a Fraunhofer telescope, finally measured the parallax of a star. His calculations placed the star at a staggering 10 light-years away, equivalent to 90 trillion kilometers. Shortly afterward, similar measurements were made by Struve and Henderson. The first breach in the wall obscuring the depths of the cosmos had been made. The discovery of stellar distances revealed that even the closest stars lay at light-years distance. Alpha Centauri, the nearest star system, was found to be 4.3 light-years away. Sirius, 8.6 light-years. This naturally raised an even grander question: how vast is the entire stellar expanse? To find out, astronomers turned their attention to the Milky Way, a luminous band stretching across the sky. Visible from both hemispheres of Earth, it suggested that the Sun and planets were embedded within a vast, flattened system of stars, a galaxy. The notion that the Milky Way was a mass of stars had been proposed as early as Democritus, but it was Galileo, with his telescope, who provided the definitive proof. I have examined the nature and substance of the Milky Way with such clarity that all controversy is settled. The Milky Way is nothing but a dense congregation of countless stars. During the 17th and 18th centuries, astronomers using telescopes began cataloging numerous faint, diffuse patches of light, which they called nebulae. These findings demonstrated that matter could organize itself not only into stars and planets, but also into enormous clouds of dispersed material. Thomas Wright was the first to propose that the stars of the Milky Way formed a vast, flattened disk. William Herschel and his sister Caroline meticulously charted stars across the sky, producing a map that revealed the disk-like structure of the galaxy. Yet, the Milky Way proved to be far more intricate than initially thought. In the 20th century, astronomers discovered that our galaxy is a rotating, barred spiral system composed of hundreds of billions of stars. Its two primary spiral arms subdivide into 5 major branches, spanning a diameter of 100,000 light-years with a thickness of about 1,000 light-years. The Sun itself resides in a peripheral region of this galactic disk, located some 26,000 light-years from the center, which harbors a supermassive black hole with a mass equivalent to 4 million suns. So, if you ever feel insignificant, consider this. Even the Sun, the center of our own planetary system and the source of life on Earth, is merely an average star in the vast outskirts of the Milky Way. But was the Milky Way synonymous with the entire universe? Observations of other nebulae suggested otherwise. Some of these nebulae, even through powerful telescopes, appeared as amorphous gas clouds rather than stellar congregations. Yet, William Parsons, using a massive telescope of his own design, discerned spirals among these structures, formations remarkably similar to the Milky Way, but seemingly positioned at extraordinary distances. Where were these spirals located? Within our galaxy or beyond it? The decisive answer came from Edwin Hubble, who turned his attention to the Andromeda Nebula. Conventional methods for gauging distance were futile. It was simply too far. Fortunately, astronomers had found a new measuring tool: Cepheid variable stars. These are stars that undergo periodic fluctuations in brightness, growing brighter, then dimmer, in a steady cycle. In 1908, Henrietta Leavitt discovered that the maximum luminosity of a Cepheid star correlates directly with the length of its brightness cycle. This relationship allowed astronomers to determine a Cepheid's true luminosity and, in turn, compute its distance. Using this method, Hubble identified several Cepheid variables in the Andromeda Nebula and calculated its distance, a staggering 2 million light-years, 20 times the size of our galaxy. The Andromeda Nebula was not a distant region of the Milky Way, but an entirely separate galaxy. For the first time, humanity grasped the true scale of the visible universe. The cosmos was not confined to the Milky Way, but extended far beyond. The revelation that other galaxies existed shattered the long-held vision of a single, static cosmos, setting the stage for a new era of astronomical exploration. The universe in the hands of physics. In the 19th century, the French philosopher Auguste Comte made a bold assertion. We may conceive the possibility of determining the forms, distances, sizes, and motions of celestial bodies, but we shall never, by any means, be able to study their chemical composition, their mineralogical structure, or the nature of organic beings on their surface. I maintain that any knowledge of the true mean temperatures of stars must forever remain beyond our reach. A strong statement indeed. And yet, science overcame this challenge with the birth of astrophysics. What can we study from distant stars while remaining on Earth? Only light. Isaac Newton first demonstrated that sunlight consists of waves of different wavelengths, spanning from red to violet. Astrophysicists learned to disperse this light into a spectrum using spectroscopes. The shape of the energy distribution curve within this spectrum allows scientists to determine a star's temperature with remarkable precision, thanks to Wien's displacement law. The shorter the wavelength of peak emission, the hotter the star. If a star's peak energy lies in the blue range, its temperature is around 20,000 degrees Celsius. Our Sun, with its peak in the green range, has a surface temperature of approximately 6,000 degrees Celsius. Red stars, by contrast, are cooler, around 3,000 degrees Celsius. These findings remain independent of a star's distance from Earth. Experienced astronomers can even estimate a star's temperature by eye, simply by observing its color. But how can we verify these spectral temperature measurements? After all, we cannot simply travel to distant stars with a thermometer, or can we? The universality of physical laws allows for rigorous testing. The relationship between spectral shape and temperature has been confirmed hundreds of times in laboratory settings. Mathematics and logic dictate unequivocally that if theoretical predictions align with experimental results, the theory must be correct. Astrophysical methods not only produce consistent results, but also yield new predictions. If there were an error in the approach, it would have been exposed long ago. Spectral analysis also reveals the chemical composition of stars by detecting dark absorption lines. Each element imprints a unique pattern of spectral lines, its own fingerprint. The presence of hydrogen, iron, and calcium in a star's atmosphere can be identified through these markers, with their relative abundances inferred from the depth of the lines. This same technique is now applied to the study of thousands of exoplanets, a field that has revolutionized our understanding of planetary systems beyond our own. The discoveries of the Zeeman and Doppler effects played a crucial role in refining these measurements. Scientists found that spectral lines are influenced by the physical conditions of the light's origin. Experiments demonstrated that certain absorption lines split into 2 or 3 components under the influence of a magnetic field, an effect first observed by physicist Peter Zeeman, a pioneer who later became one of the earliest Nobel laureates in physics. The detection of the Zeeman effect in sunspot spectra led to the discovery of magnetic fields on the Sun. In 1842, physicist Christian Doppler made another groundbreaking discovery, an effect that now bears his name. He observed that the pitch of a train's whistle appeared higher when approaching and lower when receding. This phenomenon was later confirmed in an experiment where musicians played from a moving platform while trained listeners detected shifts in sound frequency from a stationary point. A striking demonstration, but what does this have to do with astronomy? French physicist Armand Fizeau later proved that the Doppler effect also applies to light. If a luminous object moves away, its spectral lines shift toward the red end of the spectrum. If it moves toward us, they shift toward the blue. By measuring this shift, astronomers could determine an object's velocity relative to Earth. Observations revealed that spectral lines on the eastern edge of the Sun were blue-shifted, while those on the western edge were red-shifted, direct evidence of the Sun's rotation. These measurements also matched calculations based on the movement of sunspots, confirming the Sun's rotational speed. By the early 20th century, astronomers had assembled a formidable arsenal of techniques for studying celestial bodies. Giant telescopes equipped with spectrographs enabled them to determine the composition, temperature, velocities, magnetism, sizes, and masses of stars. They could even infer the properties of unseen planets orbiting distant suns. The universe, once an enigmatic and immutable realm, was now within the grasp of physics, measurable, understandable, and open to endless exploration. Through the prism of relativity. It seemed that the rapid progress of mathematics, physics, and chemistry, along with advances in astronomy, had finally provided humanity with a clear and complete picture of the universe. The task ahead appeared to be merely refining the details. Yet, by the 19th century, scientists began to encounter unsettling contradictions that hinted at deep flaws in the prevailing worldview of an eternal, unchanging cosmos. The first warning sign was the gravitational paradox. Consider this: if stars gravitationally attract one another, why don't they collapse together? The prevailing assumption had been that an infinite distribution of stars would exert a balanced force in all directions. But upon closer examination, this argument crumbled. Gravity only acts to draw masses together. There was no known force to counterbalance it. This meant that stars should inevitably fall toward one another, accelerating as they do. Over infinite time, they should have already coalesced into a single hyperdense mass. And yet, galaxies remain scattered across the cosmos without any sign of catastrophic collapse. In fact, within the Milky Way, stars move fast enough to avoid falling into its supermassive black hole. Those that traveled too slowly have already succumbed, while those moving beyond the escape velocity have left the galaxy entirely. However, most neighboring galaxies lack the necessary velocity to escape one another's gravitational pull. Eventually, they will merge. The Andromeda Galaxy, for instance, is on a collision course with the Milky Way and will merge with it in a few billion years. This paradox posed an uncomfortable question. If the universe is both infinite and eternal, why hasn't everything already merged into a single mass? Given infinite time, any process should have had ample opportunity to reach completion. This contradiction signaled that something fundamental about the notion of an eternal, unchanging universe was flawed. Another major challenge was Olber's paradox. Imagine standing in an infinite forest. No matter which direction you look, your view should eventually be blocked by trees. Likewise, in an infinite, eternal universe filled with stars, every line of sight should eventually encounter a luminous object. The night sky should be ablaze with the brilliance of countless suns, outshining even the Milky Way. Even interstellar dust could not provide an explanation. It would eventually absorb enough radiation to glow as brightly as the stars themselves. The fact that the night sky is dark suggested a profound truth. The number of stars in the universe is not infinite, or light has not had infinite time to reach us. These paradoxes, however, were only the beginning. At the turn of the 20th century, science underwent a revolution. The discovery of X-rays, which could penetrate solid matter, shattered classical assumptions. The phenomenon of radioactivity opened a window into the subatomic world, revealing the structure of atoms, a concept first imagined by Democritus. Scientists found that atoms consisted of dense, positively charged nuclei surrounded by a swarm of negatively charged electrons. Within the nucleus resided protons and neutral neutrons. Astonishingly, experimental techniques grew so precise that even individual electrons, measuring less than 1/10,000,000th of a centimeter, could be studied. The nature of light itself was finally deciphered. James Clerk Maxwell formulated the theory of electromagnetism, unifying electricity and magnetism into a single framework. He condensed all known electromagnetic phenomena into just 4 equations. From these equations emerged a revelation. Light is an electromagnetic wave propagating through space at a constant velocity. But what then was oscillating in a vacuum? The answer lay in the concept of fields. A magnet or an electric charge imbues every point in space with properties that influence other objects. These properties, described by Maxwell's equations, explain the behavior of electromagnetic fields. Moreover, these equations contained a remarkable constant, c, the speed of electromagnetic waves in a vacuum. Staggeringly, this value matched the speed of light, 299,792 kilometers per second. This discovery was nothing short of mind-blowing. It confirmed beyond doubt that light is an electromagnetic phenomenon. The universe was now understood to be interwoven with invisible fields, electromagnetic and gravitational alike. The propagation of light was no longer a mystery. Photons were now recognized as quantized packets of electromagnetic energy carrying information across the cosmos. The universe was far richer and more intricate than had been imagined even a few decades earlier. Maxwell's revelation left an indelible mark on a young Albert Einstein. In 1905, he published a paper outlining the principles of special relativity, introducing 2 fundamental postulates. The laws of physics are the same for all observers moving at constant velocity relative to each other. The speed of light in a vacuum is always the same, regardless of the observer's motion. Imagine throwing a ball forward inside a moving train. Its speed would be the sum of the train's speed and the ball's own velocity. Following this logic, a laser beam fired from a spaceship moving near the speed of light should theoretically travel faster than c. But it does not. The speed of light remains constant. This meant that time and space themselves had to adjust. Einstein proposed that time slows down and lengths contract for objects moving at speeds close to c. For the crew aboard a near-light-speed spacecraft, everything would seem normal, but to an outside observer, their clocks would tick more slowly, and their ship would appear compressed. This was no mere theoretical curiosity. Experiments confirmed it. Clocks aboard fast-moving satellites indeed run slower than those on Earth. Einstein's most famous equation, E = mc squared, revealed that mass itself is a form of energy. The implications were staggering. Even a tiny amount of matter contained an enormous energy reserve. 1 gram could release the equivalent of 20 kilotons of TNT in a matter-antimatter annihilation. This equation later explained how stars shine. In their cores, hydrogen fuses into helium, releasing energy due to a slight loss of mass. The ultimate transformation came with general relativity. Einstein demonstrated that mass warps spacetime, and this curvature dictates how objects move. The analogy is simple. Imagine a stretched rubber sheet. A heavy ball placed on it creates a dip, and smaller balls rolling nearby will follow curved paths around it, just like planets around a star. Even light bends under gravity, a phenomenon confirmed in 1919 during a solar eclipse when starlight passing near the sun was observed to shift. Einstein's ideas revolutionized science. Headlines declared a scientific revolution. His theories did not discard Newtonian physics, but expanded upon them, proving that Newton's laws were merely approximations valid in weaker gravitational fields and lower speeds. Mass, energy, space, and time were now inseparably linked in an ever-evolving cosmic dance. We are not mere observers, but participants in this vast interplay. So next time you look up at the stars, remember Albert Einstein, the man who reshaped our understanding of reality itself. As early as 1783, the astronomer John Michel pondered a profound question. What if a star were so massive that its escape velocity equaled the speed of light? His calculations suggested that in such a case, not even light could break free from its gravitational pull. Michel called these hypothetical objects dark stars. However, the scientific knowledge of his time was insufficient to develop this idea further. After all, even the precise speed of light remained unknown. It was not until 1916 that Karl Schwarzschild, inspired by Einstein's general theory of relativity, discovered an exact solution to Einstein's equations for a perfectly spherical mass. This led to a remarkable realization. A sufficiently massive star would be surrounded by a magical sphere, what we now call the event horizon. Outside this boundary, gravity behaves as expected, but once an object crosses into it, there is no return. Approaching the event horizon, an external observer would see light trapped in endless orbits around the collapsing star. Right at the horizon itself, time would appear to freeze. However, for an unfortunate astronaut falling into the black hole, no such anomaly would be noticed, at least not until tidal forces violently stretched and ultimately tore them apart. For a long time, this idea was relegated to the realm of mathematical speculation. But in 1939, Robert Oppenheimer and his student Hartland Snyder demonstrated that black holes could indeed form from massive stars once their nuclear fuel was exhausted. Without sufficient outward pressure to counteract gravity, the core of such a star collapses entirely, becoming a black hole. Today, we recognize at least two main types of black holes: stellar mass black holes, which arise from the remnants of massive stars, and supermassive black holes, which lurk at the centers of galaxies. In fact, astronomers have confirmed the presence of a supermassive black hole, 4 million times the mass of the Sun, right at the heart of our Milky Way. Were it not shrouded in interstellar dust, this behemoth would shine brighter than the moon in our night sky. Yet, the study of black holes did not end there. Quantum mechanics was soon brought into the picture. Stephen Hawking discovered that an idealized black hole contradicts the principles of quantum uncertainty. Consequently, black holes must emit radiation, what we now call Hawking radiation. This means that black holes are not entirely black. Rather, they slowly lose mass and, over immense timescales, evaporate completely. The vacuum of space, it turns out, is not truly empty, but rather a quantum soup of constantly fluctuating virtual particles. Near a black hole, one particle from a pair can fall in while the other escapes, carrying energy away. Over trillions of years, this effect causes the black hole to shrink and eventually vanish. In 1963, Roy Kerr found a solution for a rotating black hole, revealing an astonishing possibility. Instead of collapsing into a single point, such a black hole might form a spinning ring. This opened up an entirely new avenue of speculation. What if this ring acted as a gateway to another universe or another region of our own? Could it be a wormhole, a tunnel through space-time? Theoretically, wormholes could connect distant parts of the cosmos or even entirely separate universes. If such structures exist and are traversable, they might allow for faster-than-light travel without violating the laws of physics. But if wormholes one day enable us to cross galaxies in an instant, could they also transport us through time itself? Newton viewed time as an unwavering arrow, moving inexorably forward. Einstein, however, described it as more like a meandering river, flowing at different rates in different places. If we can move freely through 3 spatial dimensions, why not the 4th, time? Could there be whirlpools in this temporal river that allow for backward movement? Could the river itself fork into separate streams, creating parallel realities? The changing size of the universe. Einstein was convinced that the cosmos was static and unchanging. However, his own equations suggested otherwise. The universe simply refused to remain still. To maintain a stationary model, he introduced the famous cosmological constant, a mathematical term designed to counteract gravity and prevent the universe from collapsing under its own weight. The physical meaning and origin of this anti-gravity remained a mystery, but if galaxies appeared motionless in space, something had to oppose their mutual attraction, or so Einstein reasoned. Another intriguing aspect of his model was the finiteness of the universe. What would happen, he pondered, if one were to board a spaceship with infinite fuel and travel toward the edge of the cosmos? Would they eventually encounter a cosmic wall labeled End of the Universe? The answer was no. Instead, space itself is curved and self-contained, much like the surface of a sphere. A traveler moving in a straight line indefinitely would eventually return to their starting point from the opposite direction. Thus, while the universe is vast, it has a well-defined volume, just as the surface of Earth is finite yet has no physical boundaries. Einstein's theory deeply influenced the mathematician Alexander Friedmann. By analyzing Einstein's equations, he reached a sensational conclusion. These equations did not just describe a static universe, but also allowed for dynamic models, either expanding or contracting universes. Friedmann's model provided a straightforward explanation for why the night sky is dark. Light from distant galaxies simply has not had enough time to reach us. Gravity, in turn, was limited by either the finite mass of the universe or the high velocities of receding galaxies, which allowed them to overcome mutual attraction. Naturally, these ideas led to further questions. What existed before the universe? Why did the Big Bang occur? How does the universe compress matter into an initial singularity? Could its creation have been an act of an external force? Friedmann had no answers to these profound philosophical questions. Einstein himself was skeptical, though he acknowledged the mathematical soundness of Friedmann's equations. To resolve this debate, empirical evidence was needed. While it was impossible to conduct controlled experiments with galaxies, their motions could be measured using the Doppler effect, specifically by observing shifts in spectral lines toward the red or blue. In 1927, Edwin Hubble, armed with the most powerful telescope of his time, a 2.5-meter reflector in California, set out to test these predictions. His telescope, coupled with advanced spectrographs, could capture the faint light of distant galaxies and analyze their spectra for Doppler shifts. Hubble expected to find a chaotic distribution of velocities, some galaxies moving toward us, others away. However, reality was far stranger. While the Andromeda galaxy was indeed approaching the Milky Way at around 100 kilometers per second, all other galaxies exhibited redshifts, indicating that they were moving away. Even more astonishingly, the farther a galaxy was, the faster it receded. This pattern became known as Hubble's law. Could scientists determine when all galaxies were once incredibly close together? Yes. Hubble's law provided a means to estimate the age of the universe, the time elapsed since the moment zero when expansion began. Calculations placed this age between 13.7 and 13.9 billion years. In other words, the universe is nearly 14 billion years old. But if all matter was once concentrated in a single region, where exactly was that point? The answer is astonishing. It was everywhere. Since space itself was compressed, every point in today's universe was part of the initial singularity. There is no single center of the Big Bang. Every observer, in every galaxy, can justifiably consider themselves at the center of the cosmos. The birth of a hot cosmos. What was there before? Are you saying there was nothing, and then suddenly, with a colossal bang, the entire universe emerged from a single point? How is that possible? While ancient philosophers speculated about the fundamental elements of nature, the 20th century provided definitive answers about the chemical composition of cosmic bodies. Spectroscopic analysis of stars revealed that they primarily consist of hydrogen and helium, with heavier elements making up only about 1% of stellar material. This elemental distribution was not unique to stars, but extended throughout the interstellar medium. Why, then, is there 3 times as much hydrogen as helium in the universe? Where did this precise proportion originate? The German physicist Hans Bethe delved deeper and discovered nuclear reactions within stars, in which hydrogen nuclei fuse into helium-4. The process follows a fundamental pattern. For every 12 protons that undergo fusion, 1 helium nucleus forms. If all cosmic helium had been synthesized through stellar fusion, its mass fraction should indeed be 1/3 that of hydrogen. But there was a crucial problem. The rate of these nuclear reactions in stars was far too slow. Even over their long lifetimes, thermonuclear fusion could not have significantly altered the original chemical composition of the cosmos. This suggested that stars formed from a primordial mixture that already contained precisely 25% helium. It was the physicist George Gamow, a former student of Alexander Friedmann, who advanced this idea. By analyzing the relationship between the elemental composition of the universe and its expansion model, Gamow realized that in the first moments after the Big Bang, the density and temperature of cosmic matter were so extreme that a portion of hydrogen must have already fused into helium. However, conditions were still unsuitable for the formation of heavier elements. Building upon the laws of thermodynamics, Gamow made another profound realization. At such extreme temperatures, matter must have been in thermal equilibrium with radiation. Calculations revealed that this primordial soup of hydrogen and helium was accompanied by an overwhelming number of photons, outnumbering atomic nuclei by billions to 1. This immense photon density explained why heavier nuclei failed to form. Their presence would have been immediately disrupted by the high-energy radiation. As the universe expanded, however, the energy density of radiation decreased faster than that of matter. Over time, radiation's influence on cosmic dynamics diminished. But what happened to these relic photons? Gamow and his colleagues demonstrated that they had not disappeared. Instead, as space expanded, the wavelengths of these primordial photons stretched continuously. Initially, in the first moments after the Big Bang, they were high-energy gamma rays. But over billions of years of cosmic expansion, their wavelengths elongated into the microwave spectrum. Even today, the universe should still be immersed in this thermal radio background, a relic radiation permeating all of space. Theoretical calculations predicted that this cosmic background radiation should exhibit a temperature in the range of 0 to 10 Kelvin. Thus, the theorists had provided a clear prediction: a cosmic afterglow from the birth of the universe should exist, waiting to be detected. Yet, as is often the case in the history of science, the brilliance of this hypothesis ran slightly ahead of its time, and for a while, the scientific community overlooked it entirely. Cosmic microwave background radiation. In the mid-1950s, radio astronomers at the Pulkovo Observatory in the Soviet Union detected a faint microwave background signal with the expected spectral characteristics. However, they did not recognize the significance of their discovery. Then, an unexpected twist of fate led to one of the most profound confirmations of the Big Bang theory. While fine-tuning a receiver for satellite communications at Bell Labs, Arno Penzias and Robert Wilson encountered an unusual microwave noise. This signal remained constant regardless of the antenna's direction or the time of day. In their attempts to eliminate the interference, they cooled their detectors with liquid helium, and even went so far as to remove what they described as white dielectric material from a pigeon nest inside the antenna. Yet nothing worked. The mysterious background radiation persisted across the entire sky. Without realizing it, Penzias and Wilson had stumbled upon the cosmic microwave background radiation, the residual thermal radiation from the Big Bang. Their discovery earned them the Nobel Prize in Physics in 1978. The CMB is a direct remnant of the early universe, precisely matching the predictions of Gamow's hot Big Bang model. This radiation is isotropic and homogeneous, confirming that the universe maintained these properties even in its infancy. The detection of the cosmic microwave background became the second direct confirmation of the Big Bang theory, following Hubble's discovery of cosmic expansion. No alternative models could adequately explain the existence and uniformity of this radiation. To avoid atmospheric interference, astronomers began placing CMB detectors on satellites. The first such experiment, the Soviet Relikt, one mission in 1983, was conducted aboard the Prognoz 9 satellite. However, its sensitivity was insufficient to detect the fine structure of the CMB. A major breakthrough came in 1989 with NASA's Cosmic Background Explorer satellite. It revealed that the cosmic microwave background is not perfectly uniform. Tiny fluctuations in temperature and intensity were present. This was a revolutionary finding. The early universe was not entirely smooth, but contained minute density and temperature variations. These initial density fluctuations played a crucial role in cosmic structure formation. Slightly denser regions exerted stronger gravitational attraction, pulling in more matter. This led to an exponential amplification of density contrasts, a self-sustaining gravitational instability that gradually accumulated mass. Over time, these denser regions evolved into protogalaxies, and within them, individual clumps collapsed into protostars. As these nascent stars accreted more material, their cores ignited with thermonuclear fusion, marking the birth of the first luminous bodies in the cosmos. The second problem was the photon-baryon interaction in the early universe. In its hot, dense infancy, the universe was filled with energetic photons that continuously scattered off electrons, preventing ordinary matter from clumping together. Only when the universe cooled enough for electrons and protons to form neutral atoms, making the universe transparent to radiation, could gravitational collapse begin. However, theoretical calculations showed that the density fluctuations predicted by this process did not fully align with the structures observed in the cosmic microwave background. This discrepancy suggested that ordinary matter alone could not account for the large-scale structure of the universe. Astronomers had long noticed that spiral galaxies rotated in an unusual way. Their outer stars moved just as fast as those closer to the center, mimicking the rotation of a solid disk. This defied expectations. If only visible matter were present, the outer stars should orbit more slowly due to weaker gravitational attraction. The most plausible explanation was that galaxies were embedded in enormous halos of unseen mass. This invisible component was dubbed dark matter. Further studies suggested that the mass of dark matter must be 5 to 6 times greater than the combined mass of all visible stars and gas. In essence, galaxies resemble icebergs. Only a fraction of their mass is visible, while the bulk remains hidden, detectable only through its gravitational effects. But what is dark matter made of? Early hypotheses proposed that it consisted of large, unseen objects, failed stars, rogue planets, or black holes. However, observations quickly ruled out these ordinary matter candidates, as they lacked the necessary mass to explain the observed effects. Instead, physicists hypothesized that dark matter consists of an entirely new class of fundamental particles. These hypothetical particles, dubbed weakly interacting massive particles, are theorized to interact only via gravity and possibly the weak nuclear force, but not via electromagnetism or the strong nuclear force. This means they do not form atoms and pass through ordinary matter undetected. In fact, dark matter particles are likely streaming through your body at this very moment. An unsettling thought, isn't it? For years, the leading candidate for dark matter was neutralinos, supersymmetric counterparts to known particles. Unfortunately, searches at the Large Hadron Collider have yet to detect them. Current research focuses on alternative candidates, such as axions, sterile neutrinos, and even primordial black holes. In the early 1980s, physicist Jim Peebles realized the profound cosmological implications of dark matter. While the CMB reveals the distribution of ordinary baryonic matter in the young universe, it does not account for the role of WIMPs. Dark matter, however, had already begun clustering under its own gravitational pull before baryonic matter could do so. When baryons eventually cooled and became transparent to radiation, they simply fell into the gravitational wells formed by dark matter. Computer simulations incorporating dark matter into cosmic evolution models yielded astonishing results. The predicted large-scale structure of the universe, massive galaxy superclusters forming vast cosmic filaments with enormous voids in between, perfectly matched the observations from the Planck Space Observatory. We now understand how the universe transitioned from an almost uniform primordial state to the intricate cosmic web we see today. The remaining challenge is to directly detect dark matter particles and determine their precise nature. If experimental physicists succeed, we may finally uncover the fundamental identity of this elusive cosmic ingredient. The era of inflation and the Big Bang. At first glance, it might seem that the puzzle of the cosmos is nearly complete, that humanity has finally grasped the fundamental truths of existence. The scientific consensus now acknowledges that the universe is not static, but evolving. Yet, while some embraced this revelation with enthusiasm, others resisted, unable to abandon the comforting notion of an eternal, unchanging cosmos. Even today, there are those who challenge the very idea of the Big Bang, dismissing it as a fabrication of theoretical physics. However, even among the most ardent supporters of the Big Bang theory, there remain profound unresolved issues. Among these, the horizon problem and the apparent flatness of the universe stand as formidable challenges. One of the most perplexing aspects of the cosmic microwave background radiation is its extraordinary uniformity. Measurements reveal that its temperature is the same in all directions to an astonishing precision, varying by no more than a few hundredths of a percent. Moreover, the minute fluctuations in temperature that do exist are also strikingly consistent across the sky. This raises a profound question. Why are regions of space that are currently separated by vast distances, perhaps 90 billion light-years apart, so remarkably similar in their physical conditions? To understand why this is a problem, consider two regions of the sky, which we shall call A and B. If we point a radio telescope at A and then at B in the opposite direction, we find that the CMB signals from both regions are nearly identical. The difficulty arises when we consider the fact that the universe has only existed for approximately 13.8 billion years. Since the speed of light sets a fundamental limit on how quickly information can travel, A and B could never have interacted in the past, as the maximum distance light could have traversed since the Big Bang is only 13.8 billion light-years. In other words, there has not been enough time for these regions to exchange energy or information, making their near-identical properties deeply puzzling. This apparent paradox is known as the horizon problem. A second enigma concerns the geometry of the universe. The equations of general relativity, as formulated by Alexander Friedmann, predict that the fate of the cosmos depends critically on its average density. If the density exceeds a certain critical threshold, gravitational attraction should eventually overcome the expansion of space, causing the universe to collapse back upon itself. Conversely, if the density is too low, the universe should expand forever at an ever-accelerating rate. However, observations indicate that the universe's density is astonishingly close to this critical value, leading to what is known as a spatially flat universe. Although Einstein originally introduced the cosmological constant into his equations to maintain a static universe, a move he later regarded as his greatest blunder. The concept of a repulsive force inherent to space itself found new life in the context of cosmic inflation. The key idea of inflation, first proposed by Alexei Starobinsky and later developed independently by Alan Guth, suggests that in the earliest fraction of a second after the Big Bang, the universe underwent an extremely rapid exponential expansion. This expansion stretched space so rapidly that regions that were once in close causal contact were flung apart, solving the horizon problem in a straightforward manner. Prior to inflation, all the regions of the observable universe were indeed connected and could have achieved thermal equilibrium before being driven apart. Inflation also provides an elegant solution to the flatness problem. As the universe expands exponentially, any initial curvature is rapidly smoothed out, just as the surface of an inflating balloon appears flatter and flatter as it grows. This effect ensures that, regardless of the initial conditions, the universe we observe today appears nearly flat. But what could have driven this inflationary expansion? The answer lies in the peculiar properties of quantum fields. Physicists now understand that even empty space, what we call the vacuum, is not truly empty. Instead, it is filled with fluctuating quantum fields that can possess energy. In the context of inflation, this energy is associated with a hypothetical scalar field, sometimes called the inflaton field. When the universe was in its earliest moments, it is believed that this field was trapped in a high-energy state known as a false vacuum. A striking feature of this false vacuum is that it exerts negative pressure, which leads to a repulsive gravitational effect, a kind of cosmic anti-gravity. This anti-gravity effect was so strong that it overcame the usual attractive force of gravity, causing space to expand at an exponential rate. During this period, any irregularities in the initial distribution of energy were smoothed out, creating the remarkably homogeneous universe we observe today. However, inflation did not last indefinitely. The high-energy vacuum state was not stable, and eventually it decayed into a lower energy state in a process known as reheating. When this happened, the enormous energy stored in the inflaton field was converted into a hot, dense mixture of elementary particles, quarks, leptons, photons, and neutrinos. This transition marks what we traditionally call the Big Bang, the moment when the observable universe was filled with matter and radiation. With the end of inflation, the anti-gravitational force disappeared, and the universe's expansion slowed down, becoming governed by the normal laws of gravity. However, the momentum imparted by the inflationary phase ensured that the expansion continued, leading to the formation of galaxies, stars, and planets over the next billions of years. Today, inflation remains one of the most compelling explanations for the structure and evolution of the universe. It not only resolves the horizon and flatness problems, but also provides a natural mechanism for generating the tiny fluctuations in density that later gave rise to galaxies and cosmic structures. These fluctuations, imprinted in the CMB, match the predictions of inflationary theory with remarkable precision, lending strong support to the idea that our universe was once a minuscule, causally connected region that underwent an astonishing phase of accelerated expansion. Dark energy, the accelerating universe. As we've already seen, Edwin Hubble determined distances to nearby galaxies using standard candles, astronomical objects of known luminosity, particularly Cepheid variable stars. But how could astronomers measure distances to far more distant galaxies, which appear as mere faint smudges, even in the most powerful telescopes? In 1977, astronomer Yuri Skovsky proposed using Type 1a supernovae as such beacons. These cataclysmic explosions occur when a white dwarf reaches a critical mass and undergoes a thermonuclear detonation. Their brilliance rivals that of an entire galaxy, making them visible across vast cosmic distances. Though rare, they appear frequently enough within the observable universe to serve as reliable markers. In 1998, Brian Schmidt and Adam Rees published a shocking discovery based on 16 Type 1a supernovae. Their brightness was lower than expected for their measured redshifts, meaning these galaxies were farther than anticipated and receding faster than predicted by Hubble's law. The expansion rate of the universe was not slowing down as expected, it was accelerating. A year later, a team led by Saul Perlmutter confirmed this result with observations of 42 more supernovae. Something was driving galaxies apart with ever-increasing speed, as if a repulsive force, a form of cosmic antigravity, was at work. In 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for this discovery. Previously, the primary debate was whether gravity would eventually halt cosmic expansion, leading to a contraction and possible Big Crunch. Now it became evident that the universe's expansion was not only continuing indefinitely, it was accelerating due to the dominance of this mysterious repulsive force. What, then, is responsible for this acceleration? Scientists named this enigmatic force dark energy. Early hypotheses about its nature drew from inflationary theory. Recall that after the Big Bang, a high-energy vacuum transitioned into an ordinary vacuum with nearly zero energy density. The observed acceleration suggests that this vacuum energy is not entirely negligible. In fact, it may correspond to Einstein's cosmological constant. In this model, dark energy is a fundamental property of space itself. It is uniformly distributed across the cosmos, permeating both the vast voids between galaxies and the interiors of stars. Its density remains constant over time and does not interact with matter in any conventional way. Calculations indicate that around 7 billion years ago, the average density of matter in the universe fell below the density of vacuum energy. From that point onward, dark energy became the dominant force, driving the universe's accelerated expansion. Astonishingly, for over 2,500 years, astronomers have been studying just 0.5% of the universe's total mass. But what exactly are dark matter and dark energy, which together comprise the vast majority of our cosmos? The truth is, we do not yet know. However, scientists are actively exploring theoretical models that may soon illuminate these mysteries. In search of answers, where did the primordial bubble of ultra-dense vacuum that gave rise to our universe come from? Could it have emerged from the depths of another reality? And does that parent universe still exist? Perhaps, even within our cosmos, new universes are constantly being born? The honest answer for now is that we do not know. But science has some intriguing ideas. For physicists, the appearance of fluctuations in high-energy vacuum is not an insurmountable mystery. If we could magnify the quantum realm by a factor of 1 billion, we would witness a ceaseless dance of virtual particles, ephemeral packets of matter flickering into existence and vanishing almost instantly, much like fleeting morning exercise resolutions. Normally, these virtual particles annihilate each other immediately, releasing energy in the form of light. However, in the presence of a sufficiently strong field, they can be separated before their mutual destruction, effectively becoming real particles, emerging, seemingly, from nothing. In reality, they are manifestations of the energy stored within the surrounding field. This quantum foam is a turbulent sea of possibilities, occasionally birthing highly unstable particles, including those corresponding to an unstable vacuum state. A single quantum fluctuation, under the right conditions, might be enough to trigger the expansion of a hidden pocket of space-time into an entire universe. But how could such an infinitesimal region contain enough energy to power the Big Bang? To understand this, consider black holes. From the outside, they appear compact, yet their interiors harbor enormous mass energy densities. Gravity compresses vast quantities of matter into an incredibly small volume, storing an unimaginable amount of energy, enough to distort and even rupture the very fabric of space-time. If this is true, then even an externally minuscule object might, due to its internal geometry, contain an entire universe with immense energy. Could our cosmos itself be the interior of a black hole within some grander external reality? This is not an unreasonable proposition, though it remains unproven. Theoretically, a highly massive, exotic particle, sometimes called a Friedmann, could also encapsulate an entire hidden universe. To an external observer, such an object would appear as a fleeting quantum fluctuation, while within, it could endure for trillions of years. If so, could microscopic universes be continuously forming within our own cosmos? Paradoxical as it may seem, this is a genuine possibility. Skepticism is understandable. One might think this sounds like pure speculation, yet physicists take these ideas quite seriously. One of the most compelling models for universe formation was proposed in 1983 by physicist André Linde. According to his eternal inflation theory, an exponentially expanding parent universe continuously spawns new microworlds with ever-growing distances between them. This process results in an uncountable family of universes, each potentially undergoing its own phase of inflation and subdivision. The implication is staggering. There could be an infinite number of universes. In this framework, our cosmos is merely one bubble within the vast, foamy expanse of the multiverse, an endless spectrum of parallel worlds. The multiverse concept also provides a compelling answer to a fundamental mystery. Why does our universe appear so finely tuned for life? If we survey all conceivable combinations of fundamental constants, from particle masses to the values of fundamental forces, most of them would render a universe utterly inhospitable, devoid of atoms, stars, or planets. It almost seems as if the universe has been deliberately calibrated for observers like us. One could imagine an advanced civilization that deliberately tuned our universe by initiating inflation within a precisely crafted vacuum fluctuation. Perhaps one day, even humanity will learn to engineer micro-universes by manipulating controlled matter collapses. Alternatively, there is a simpler explanation. If the multiverse produces every possible configuration of fundamental laws, then among this infinite variety, somewhere a random fluctuation will inevitably generate just the right conditions for the emergence of complex structures, galaxies, planets, life, and intelligence. From this perspective, our universe is not special. Rather, we exist because it is one of the rare cosmic settings where life can emerge. Were the conditions any different, we simply wouldn't be here to ask these questions. The multiverse hypothesis is undeniably mind-expanding. If it is true, then somewhere an immortal version of me may exist. In this universe, I am still working on it. Yet, not all scientists accept the multiverse as a legitimate physical theory. A robust scientific hypothesis must provide a way to be tested experimentally. However, by definition, parallel universes cannot interact with our own, making their existence fundamentally unverifiable. No experiment, thought or real, can directly detect neighboring worlds. So, should we even take this idea seriously? On the other hand, modern physics frequently encounters theoretical constructs that do not outright contradict known laws, but remain beyond direct experimental reach. For now, we seriously consider dark matter, primordial black holes, and wormholes, despite our inability to observe them directly. The multiverse and higher dimensional space-time should at least be regarded as promising frameworks awaiting future breakthroughs. At this very moment, cutting-edge computers are simulating the most complex models. Telescopes tirelessly scan the heavens. Particle accelerators probe the depths of the quantum realm. Scientists continuously test their hypotheses against the growing body of experimental data, inching ever closer to a fundamental understanding of reality. Yet skeptics remain vocal. So scientists still don't have definitive answers about the most basic questions. What caused the Big Bang? What existed before it? What is dark matter and dark energy? How many parallel universes are there? And most importantly, should I take an umbrella today? Yes, our knowledge is still incomplete, but it is expanding. Since the days of Giordano Bruno, our understanding has grown by orders of magnitude. We are now seriously debating hypotheses that attempt to explain dark energy and dark matter, speculating about the multiverse, and grappling with the paradoxes of the anthropic principle. But these remain hypotheses for now. Further research, whether tomorrow or in 400 years, will uncover the answers to these and countless other astonishing questions. Science will find them. It is difficult to even imagine what discoveries await future generations. They will look upon the ideas of the 21st century as we now view the speculations of the Middle Ages. And in a few decades, even this discussion may be hopelessly outdated. A delightful prospect,